Okay, so this is part 2 of performance monitoring basics. I know one so far who has actually gone on the internet and seen the first part. Did anybody else go on the internet and see the first part, or does?
Yeah, we did last week.
I got to see it live.
Yeah. So everybody remembers pretty much the discussion we had. Do you want me to go over a couple of the finer points? Just a high level overview. Do you want me to start off almost exactly where we started, where we left off?
Right where we left off.
Right where we left off. Excellent. There are a couple house cleaning items that I want to take care of first. First off, Joe asked a question last time about the difference between TS kill and task kill, because if you remember, TS kill gives you the permission denied or the access denied when you go to kill certain processes. And I didn't really have a full answer for him then, but I do now. I talked to Mark Rasinovich at Microsoft, and he's the guy that wrote the sysinternals tools that we were talking about last time. And he wrote Process Explorer and all those things. And he told me that the reason why is because TS kill and task kill are for two different audiences. TS kill goes through the process security layers in order to see whether or not it has permissions to kill a process. And if a process is running under a different user account, say like in the case of SQLwriter, where I was trying to kill SQLwriter on my current box, it was running under local system, and I'm clearly not logged in as local system. So therefore, it failed with access denied because it didn't have permissions. It went through the permission stack. But task kill doesn't go through the permission stack, so it's able to assert its forcefulness on the task process and actually close the task of a different user. So that's why that was able to work. And he also asked which one of those two processes that Task Manager uses, because I showed you that you've got Task Manager, which is the GUI tool, and those two are the command line tools. And it turns out that whereas I would have thought that it may have called one of the two others, it really just they all make calls to the same OS primitives. So there's a Windows API that they all call. So it's not really that Task Manager uses one of those two command line tools. It's that all three of those tools call the same OS primitive, because there's only one primitive to be able to call, right? So I'm glad Joe could be here to get that answer. Maybe he'll watch the video.
How are they?
And there's one other thing I wanted to show you here that I forgot to show you last time in Perfmon. And one of these is going to be the source of one of the confusing points that I alluded to last time, right? So as soon as I can bring this up, there we go. You'll notice every time you bring up one of these, every time you bring up one of these performance objects or performance classes, right? That it's got one of the things that are highlighted. See, and it's not always the first one, right? So what that is, oh, good timing. So so what that is that's a suggested counter, a suggested general counter for monitoring that class.
Most usually used.
Yeah. So you'll notice, like when you go to, see if I can find it here, system, file data operations per second. That's a little vague, isn't it? Here's the one I want right here, processor. Percent processor time. That's the one most people use, right? I mean, right off the bat, you want to see whether or not you've got high utilization on your CPU. So all of these are suggested counters, and it's not always the first one. Joe, you'll have to go back and watch the video, because just before you got here, I explained. I researched and got the answer to your questions, the difference between TS kill and task kill.
Oh, I'm telling.
From last time. Yeah, Carl's good. Carl can tell him.
That's some privilege, something.
Exactly.
Aboriginal, you know how that works, right?
Is that?
Aboriginal. Primitive. It was a stale pun, just like. Okay. Now on to now we're going to start off directly where we left off last week. And the easiest way to do that is to just go ahead and pull up. Well, I'll leave Parfmon open. I'll probably need that, huh? Let's see if I can find this here. Where were we? Okay. We started off directly with the 9 direct disk counters that get measured by the disk perf measurement layer. The cool thing is that there are only these counters that exist as raw data. Everything else that is a disk counter is derived from one of these counters through some sort of small equation, right? So I could read you this entire exhaustive list, but it's up here on the screen, so I'm not going to bother, right? And we tend to run out of time anyway. So with every other counter being derived from these counters, there are some things that that you will need to do when you're looking up, when you're analyzing your counters, right? And that's one of the things that these external tools do for you guys, like Quest Spotlight and HP OpenView and MOM and those guys. What they should be doing, and I'm sure they do, that's the value they add, is you don't have to do these equations yourself. Typically in a scenario like this, when you're using Perfmon, the poor man's performance monitoring, right? You'll save these guys to a log file, and then you'll import those into Excel, and then you have to plug in all your own equations for every one of these that you want to calculate, and if you want any real numbers. And so that's where these guys add the value at $1,000 a CPU, is in doing some of these equations for you, which are easy enough to look up in the res kit and other books, right? So one of the things that I was talking about last time is the misleading disk counters, and the big misleading disk counter is percent disk time. A lot of people go by what it says in the Perfmon explanation, which is percent disk time is the percentage of elapsed time that the selected disk drive was busy reading or servicing and read or write requests. If I could read, it would help, right? But the calculation used to derive the counter isn't based on service time or disk utilization. So what almost every admin looks at as percent disk time is just what it says there, the percent of time that the disk spends servicing the request. And unfortunately, that's a mistake. The developer that originally wrote that made a mistake in the disk perf layer that I showed you in the diagram before that sits between the request layer and the driver. That disk perf layer, what it does is it calculates the total time for a round trip. Okay, so as it comes down the stack, here, let me open that back up for you because it's easy. It is right there. And it opens. There we go. Okay. So I've got this guy right here, and we're talking about these guys right here, right? The logical and physical disk measurements. Now, as the request comes down here, it passes through these guys, then it goes all the way down to the disk, does its thing, and then comes back up and gets counted again on its way out, and it gets timed, okay? You can easily see that this isn't service time because this is going to include any queue time, any wait time, anything, right? If there's a large queue time and this has to wait for 30 minutes, the disk didn't spend 30 minutes servicing that. It spent 30 minutes in a queue, and it spent 10 milliseconds servicing it, right? So unfortunately, the percent disk time is calculated using that, and it's very misleading what that's actually for. Do not use percent disk time to calculate service time. Okay? You will be sadly disappointed. Yeah, and this goes into the whole explanation here that the formula for utilization is service time times the I/O arrival, or the completion rate. And the developer thought he was calculating that initially, and the mistake is that service time isn't what's being measured with the disk perf layer. the equation is response time times arrival rate. And that's actually what's known as Little's Law. That's pretty easily looked up on the internet with lots of explanations. But Little's Law is a basic disk queuing calculation, is basically what it is, right? And you don't need to look up Little's Law. If you want to, you can. But just know that it's a basic disk queuing calculation. That's actually what's being used there. So and this is the way that percent disk time is actually calculated. For a single measurement interval, it is the percent disk time is the minimum of read plus write times 100 divided by the duration of time. Now you'll notice this little 100 right here that I didn't mention. That means that they're capping it at 100. And in NT4 they started capping that at 100 because with queue times, and this is where the percent disk time becomes kind of invalidated as a servicing measurement, because without that, with queue times and wait times and all of the other things that go in there, you can easily get a percent disk time over 100% on a busy system. So they give it a false cap at 100 so that it never shows over 100, because admins were going 112%. What does that even mean? How can a disk be more than 100% utilized?
Overclock.
Yeah. No. Mark Friedman at Microsoft, who wrote the performance guide and the 2003 resource kit, told me that this was capped at 100 in NT4 and in 2000 and in 2003. But I have seen percent disk time over 100% in Server 03. So I think they've removed that cap, and he just didn't know about it. But all the same, if you see it over there, just realize that that's what it is. It includes wait times and.
Okay, so if that's not an accurate metric, what can we look at to get a better handle on how much of this
On service time,
is actually spending on servicing requests?
we're actually covering that.
Okay.
I wouldn't tell you that the counter sucks without telling you a way to actually calculate it, right? So the easy way to do that is just to do 100 minus the percent idle time, because idle time is being calculated correctly because it doesn't go through. I mean, there's nothing going through there, right? It's like, what's the value of a null sort of thing, right? So if you take the idle time and subtract it from 100, which is 100%, then you'll get the actual disk service time. Fair enough? Which is, again, one of those little equations that you have to plug in yourself that hopefully one of those value-added programs would do for you. Now, and here I talk about Little's Law again. Yeah, so they had this problem with their percent disk time. And so in NT4, that's when they introduced the percent average disk queue length. And then that is actually directly applying Little's Law. That is a direct application of Little's Law right there. Which again, were you here for that, Joe? Which again is just a queuing equation. It's a basic queuing equation. And that allowed them to effectively remove that artificial cap on percent disk time. And unfortunately, the really, I want to say gross part, but the really gross part about it is that error is still there. I mean, that error in percent disk time has been there since like NT3.5, and it's still there even in Server 08. It hasn't been fixed. So I don't know when or if they're ever going to plan to fix it, but it's not fixed yet. So just don't use percent disk time. It really isn't going to tell you much, especially for the high level stuff that you're going to be doing, right? Now, before we get into specific counters, does everybody know the difference between a logical and a physical disk counter, or a logical and a physical disk? Because when you go into perfmon, I don't remember if I discussed this last time. It's been a couple weeks, right? My lovely box takes forever to open everything up.
We talked about it last time.
I talked about it last time? Okay, okay, good. And everybody remembers, because there are some people that weren't here and whatnot. Okay, good. So everybody knows what physical and logical disks are. Good, explain it to me, because I can't remember. So you've got a few simple disk perf equations here. Disk utilization is 100% minus idle time. Service time is utilization plus average disk transfers per second, right? So you can tell how long it's taken the disk to actually service the request. And then Q is average disk seconds per transfer minus disk service time. So you can see that you've got calculations that rely on other calculations that rely on other calculations. Sometimes it builds, right? No. Solving disk issues. Did we talk about disk queues last time and what disk queues actually mean and how to tell what a good disk queue is versus a bad disk queue? We didn't talk about that? Okay. Of course, a disk queue is simply when you've got a line of work to do, right? It's a queue. You got a line of work to do, and the disk can't keep up with it, so it puts it in a queue and services it as it comes in, right? It's a to-do list, okay? And there are three ways that I know of to figure out what the disk queue is, okay? And in varying orders of complexity and accuracy. And oddly enough, the absolute most complex is the most accurate, and it's the one you will never, ever use. I've used it like once, like 10 years ago, and said, oh yeah, this is BS. So the best way to do it is there's an equation that I'd have to look up because it's been so long. But there's an equation where you get the advertised disk performance stats from the vendor, okay? The theoretical stats from the vendor, you get your actual stats, and then you compare, and then you plug them into an equation, and it tells you what your acceptable disk queue for that model of hard drive is, and that will change for every model of hard drive. It's extremely accurate and extreme overkill. Nobody will ever do that. Okay, I'd be surprised if they even did that for these big benchmarking systems where they're trying to find the fastest SAP system in the world. I doubt very seriously that they calculate disk queues to that level, because it's just not necessary, okay? The second way, and the one that you're going to use most of the time, is you just average at 2 queues per spindle, okay? So a spindle, if you look at hard drive architecture, I'll tell you why it's called a spindle. You've got platters, and you've usually got a stack of platters, right? And you've got an actuator arm in there that moves, and sometimes it moves in between the platters. That little rod that all of the platters are stacked up on, that's the spindle. Okay, the axis is the spindle. So, or the axle. So, for every physical hard drive that you have in your array, every physical hard drive, you can afford a disk queue of 2 without being concerned. Okay, so if you have an array of 30 spindles, then you can have a queue of 60 before you get concerned. So it's just the number of spindles times 2, okay? And it really throws somebody sometimes, because on systems like ours, where we've just got, hundreds of disks in our SAN, you can have a disk queue of, 1 and 200, and you do them out. Well, it's okay, it's still okay, but it doesn't seem like it should be, because that's a big disk queue, right? But it's perfectly fine. And that's when you need to know the difference between physical and logical, because if you're looking at your logical counters and you've got, 12 on one, if you've got 3 partitions on a hard drive and you've got 12 on one and 8 on another one and 5 on another one, well, that's a disk queue of 25 on a single spindle, right? Forget the logical partitions, that's a single spindle, okay? So if you don't know how many spindles you have, man, the barbecue's kicking in. It's heavy, man. If you don't know how many spindles you have, and you're looking at your disk queues and you see that you've got disk queues of 50 or 75, then you need to find out how many spindles you have. I mean, just flat out, you need to find out. You need to call your disk guys and say, okay, how many spindles do I have in this array? If it's, 20, and you've got a disk queue of 75, yeah, you've got a disk queue, right? So, and if you don't know, Geez, that's a tough one. If you if you just can't find out from anybody how many spindles you have, then you can say, well, 50 is usually high, so I'll go with that and say it's a disk problem, and I'll start going down that road. I mean, well, what other choice have you got, right? What other choice have you got? It's like when people come to me and say that, well, the system is really busy. We're at 89% CPU. Well, how much is it usually? I have no idea. Then how do you know we're in trouble? But 89 is kind of a high CPU for most systems, so I can go ahead and look into the high CPU angle and see if anything is wrong, right? Well, everything seems to be humming along, and I don't see any huge wait times, and there's no CPU queue. There are no waits in SQL. There are no other OS waits. It's not causing any kind of disk contention or anything, or any disk queues or anything. So it's a little high, but it seems to be running okay. So let's leave it alone and see if we have any problems, right? There's not really much else you can do. And the third way that you can calculate disk queues, and I don't think this one's much in favor anymore. This one was in favor about a decade ago, and a lot of people used it to varying degrees, but it's really not that accurate, and you'll see why when I tell you what it is. I just don't use it anymore. But the third way is to calculate a disk queue of 2 per CPU. So for every CPU, you could have a disk queue of 2, which you can see that's a lot less accurate. It's a lot less accurate. So you could have a 32 CPU system with 1 spindle, and if you want to get stupid about it, right? But it's just not that accurate. But it did used to be used by quite a few people, so I still mention it. If I don't know the number of spindles, and I've got a disk queue of 50 or 100, and I don't know it at all, then I'll take that and I'll look at the number of CPUs, and I'll do the math on both of them, and by both measurements it's a little high, so I'll go ahead. I may use it just kind of a vague, very, very vague guideline, but it's not a good one. But I thought I'd throw that out there because you may hear it. Okay, so once you decide that you have a disk queue, and it's something that you should be concerned with, you've got to figure out how to fix it, right? And I can't remember if I put these in any particular order or not. Maybe just the order I thought of them in.
How do you know how many disk queues you have set up at the time?
What do you mean?
We said, what if you have 10, 50, whatever.
Come in here, and here you've got the average disk queue, okay? And we'll do physical because it's closer. But here you've got, in Perfmon you've got your average, but you've got your average for read and write, and you've got my favorite one, which is current, because database processes are a lot easier to look at sometimes than other processes, right? Because you can look in the database tables and see exactly what's going on in the database, and then you can see the exact disk queue here, and you can see if that's causing a problem, right? Other Windows processes don't really have that luxury, but we do. So current disk queue, I like that better when I'm physically watching, when I'm sitting here just actually watching it, okay? Because the average, you'll see the current disk queue could jump up to say, the current disk queue could be 5 and it could be sustaining at 5. But I may have just finished a long process and the average disk queue could be 150. Because it had higher disk queues before, and those went into the average. And now it's dropped, but it's dropped the average a little bit, and the average will start to curtail, right? It'll start to taper. But until it does, you still think you have a really high disk queue. So I like the current disk queue because it's an instant snapshot. And every time I log performance counters to a file, I always take the average and I take the current disk queue because I also like to take an average of the current disk queue as well. Okay, that way I'll know what the interval is, because if I'm logging these every second or every 5 seconds, and I've got these in my Excel file, and I can highlight a time range and see what the average disk queue was from my current disk queues for that specific time range, instead of having to say, okay, well, this was this, and do some kind of weird delta thing in there and try to figure it out. I know exactly what it was because I'm feeding the raw data in there myself. See what I mean? So I like to use the current disk queue, and there is no current disk read and write. It's just a current disk queue. But yeah, I'll also grab the read and write too, because you'll want to see there's the read queue length and the write queue length is lower. Because once you determine that you have a disk queue, you'll want to see if it's a queue with reading or writing. That'll tell you whether or not you're having problems with, say, bulk inserts or index reads, right? So one of the first things you can do when you have disk issues, especially at the Windows level, not as much at the database level, because we're talking about two different types of defrag, right? Is you can defrag your hard drive. And that gets overlooked by so many people. It's one of the easiest things you can do. It gets so incredibly overlooked. Nobody ever even thinks defrag anymore. And I don't know why. But defragging is extremely important. Does everybody know what disk fragmentation is? What causes it? Everybody's up on disk fragmentation. Okay, good. So simply defragging is a really good way to decrease, and simply what defragging does is it decreases the reads and writes, and you have fewer reads and writes, so you do things in more operations, or in fewer operations, and your disk queue goes away, right? If you've got Windows reads in 64K chunks, okay? So if you've got a file that you need to access spread across, if it's a 64K file and you've got it spread across 8K chunks, right? It's got to do 8 different reads to get that, whereas opposed if it were in one single defrag chunk, it could do it in one read. I mean, that's just the simplicity of it, right? So defragging, excellent.
Is defragmentation available on SANs?
Yes. And there are some really good online. Now, the funny thing is there are some people that will tell you that there's no such thing as defragging like a RAID 5, because the very nature of RAID 5 is fragmentation, right? Because it's splitting that thing across several different drives. But that's just BS. I mean, yeah, it's going to split it across there, but it's going to split it across in an ordered fashion of the same size chunks in an orderly fashion. Whereas if you did 2K here, 1K there, 2K there, 2K there, 2K there, yeah, there's a big difference, right? And if it wraps around and has to go back to this one when it ordinarily would have only fit on 2 of them or the 4 of them, right? So, so there's a difference. But to answer your question, yes.
Because one of the things I know I always ran into with network people when I was doing DBA type activity, it's like, nope, we can't defragment the SAN. They won't let us. The SAN vendor won't let us defragment it.
Oh, really?
And I'm sitting there going, excuse me, what? Yep. Now this is a few years ago.
Yeah.
That's why I was curious if it's changed.
Well, I have no idea what the policy of the vendors has been over the last few years. I've never asked.
I mean,
I've always just done it.
RAID 5 is fine.
Right.
But that's not a SAN.
Right. Well, I don't know why they wouldn't want that. I know some people. I know the guy that writes Disk Keeper, so I'll ask him. Yeah, that's an interesting question. I'll ask him why a SAN vendor wouldn't want you to do that.
And at the same time, you made an interesting comment a few minutes ago with respect to defragmentation, disk, and database. And it is true that unless you get really lucky and your database is taking up your entire drive,
Right.
you do
Right.
benefit from defragmenting.
Oh, absolutely.
of the
Absolutely.
database level.
I just didn't want to confuse.
Okay.
We've got enough people in here that speak databases that I didn't want to confuse database table level defrags with OS level defrags, because right now we're talking about pure Windows, right? And yes, absolutely. When you've got especially more than one log file, more than one database file on the same partition, and they're set to auto grow, which most of the time they are, because you don't want to run out of space for something stupid, right? Then they're going to auto grow over each other like that, right? So yeah, you're going to get fragmentation, absolutely, yeah.
Which then comes back to the same question.
Yes, it does. Now, I did an exercise a few years ago where I purposely fragmented database files, just to fill in on what you were saying. And I wrote a routine that grew the database by 1 meg as it wrote. And I purposely severely fragmented it. So I must have had that thing in just a gazillion fragments. I mean, I let that thing run for like 3 hours with 70 users and just bam, 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 bam. It just fragmented the hell out of it. And then ran a workload against it. And then I defragged it. And I ran a workload against it. And I got something like 2,500 times performance increase. I mean, it's phenomenal. I mean, the difference is just amazing, right? So, yeah, and that comes out in number of reads and disk service time and disk queues and all. I mean, all of those things just start lighting up. I mean, you get just this big linear Christmas tree in perfmon that just goes, all right. Something else I didn't show you as long as I'm here, and I meant to put that in the house cleaning section, but I forgot. When you get a lot of counters in here, it's really, really hard to see. I mean, yeah, you can highlight this guy here. And as you go through here, it's probably processor. There you go. You can highlight which one you're looking at, but if you get 40 or 50 counters in here, which really isn't that uncommon, it can be really hard to see. So switch it over here to log view, and they'll just go down like this, and then you can just look at this column of numbers and see which ones are out of whack. It's much easier to see if you're doing this real time, right? I've got a and then there's this guy right here, which I don't like either. I've got let's see if I can find it, a picture somewhere, I think it's here, of, where's my nasty perfmon? I did this a while back, and I can't find it. I thought it was in here. It was, oh, there it is. It's my nasty perfmon that I did from our environment here when I added all of the discounters for all of the warehouse disks, and I just wanted to see what it would all look like in perfmon, and that's just ridiculous. And that's with highlighting turned on. I mean, it's ludicrous. So you can see they get pretty messy. You can't see a thing in there. So anyway, so that's fragmentation. Now we're to read and write controller cache. I suppose we could shorten this up and say, okay, does everybody know what read and write controller cache is? I know you do.
So.
Okay, on the controller, which is the card that interfaces with the disk, right? It's what you actually plug into the disk in the back, right? There is a caching mechanism on there, okay, and it's usually battery backed. If it's not battery backed, then don't use the cache, right?
Especially on the right level.
Yeah, especially on the right level. Yeah, read level, not that important. So this, oh man, I know what I meant to do. There was an example I found that was just phenomenal that explains the difference between disk seek time and memory seek time. Okay, and I meant to find this, and I'll extempore it. I'll kind of I'll give you the example without giving you the exact numbers, but it's pretty close. For disk latency, or for memory time, if you expanded the memory time into, say, minutes instead of nanoseconds, okay, for a memory lookup in cache, it takes something like 2 or 4 hours to look up a piece of information in memory. Okay, that same pull off of disk takes like 40 days. If you were to put that in minutes instead of nanoseconds, it was an incredible thing that really shows you the difference between a disk lookup and a cache lookup. Okay, God, I wish I wrote that down. Anyway, so cache, a disk cache is just what it says. It does prefetching and it does the disk lookups before you get to it. Right? We're talking about read cache now. Say it'll do a read ahead if you're doing a table scan, right, or a table lookup. I'm going back to databases. Sorry, but it'll prefetch and it'll pull that data from the disk into the cache, so that by the time you need it, it's pulling it out of the cache instead of having to wait for the disk. Okay, and it will greatly improve your read access by many thousand times. Okay. The same thing with the write access, or with the writing cache. And the writing cache is really important, especially in an OLTP environment, because in order for a transaction to go back to whatever client it is, it doesn't matter, right? But we deal with it on the database level. But for a client to receive a transaction complete, it has to actually be written to disk, okay? Which means, going back to our analogy, you have to wait the 40 days and then send it by messenger back up to the application that says, okay, it's complete, right? Well, write cache saves it in cache like that, and then shoots off the reply that says that it's finished. And then in the background, it saves it to the disk. So the client doesn't have to wait for the full round trip to the disk every time. It only saves it in the disk cache, and then the disk cache goes ahead and replies and says, yes, I wrote it. It's on the disk. The client doesn't know the difference. The cache says, yes, it's on the disk. And then it goes in and writes the disk. Now you can see why having a battery on that is very important, because if it goes down, if your controller goes out, right, then you're going to be up the creek, right? Because you've got committed transactions that haven't been committed. So
Is there a size for that case?
yeah,
Regular size?
well, the size is in percentage. The size that you can configure is by percentage, right? If you look at disk drives, when you see them in the store, if you go to Fry's and you go get a disk drive, it'll say like 2 megs of cache.
Oh,
That's what it means. Okay. Now inside of there, for RAID controllers, you can go in there and you can set the level of cache, right? For most home controllers, you can either set it to read, to write, or to read and write, which is going to be 50% of each, right? So you're going to get a meg each of that.
so
For
every incomplete operations, when we open a Word file, I was trying to save, but it didn't save. So it is reading from the cache, you mean?
I'm sorry.
It is incomplete, for every incomplete operations, like right for saving any file. When I tried to save a file, the power shut down. I was not able to save it into the disk. So it reads from that write controller case. Next time when I turn on the computer.
Oh, from Word? From your laptop? No. Word keeps its own temporary files. Yeah, that's a different mechanism at work there.
Oh, okay.
You don't really have control over the cache on your box, and I don't think a laptop like this even uses write cache. I think they just use that for prefetching read cache.
Interestingly enough, though, you will see every once in a while a message come up out of Windows, the delayed write failed, and that's actually at the OS level, not at the hard drive level.
Exactly. Now, at a professional level, when we get into these $20,000 and $50,000 RAID controllers, right? you can have some pretty fine, detailed control over some fine-grained control over your read and write cache, right? You can have 100% of each, or you can say 90 and 10, or 50-50, or 70-30, whatever, right? So, optimally, if all we had to do was load up and run an SIS package every night and just load your warehouse, and you didn't have to do any lookups from this database on the same system or anything, you could get a lot higher load. You could finish your load much faster if you switch it to 100% write cache during the load and then switch it back to 100% read cache right afterwards. But of course that has to be done at the RAID controller level, which means it takes a reboot. You have to reboot. You have to go into the RAID controller while you're rebooting, and then come back up, and then you have to reboot it again afterwards. It's just not worth it, right?
Yeah, but I mean, given the analogy that you just gave, you're going to overrun your write cache under those circumstances anyway. I mean,
Yeah, you'll overrun your write cache, but you.
So at some point, you're not going to get any additional value out of it.
It depends on how much write cache you have and how
Fair
fast
enough.
it does the write behind,
Fair enough.
right? But we did have a system at my last gig where we turned it on 100% write. It makes a significant difference. I mean, it really does. So, how and when to set it, I think we've kind of covered that. Leave it at 50% most of the time. I mean, unless you've just proven that you're not doing hardly any reads at all and you're just 100% writes, 90% writes, then yeah, take the small hit on the read aheads and do it 100% write cache, and you'll be great. your system will never perform better, right? Same thing the other way around. So,
Is it, you actually raised a very interesting point there. Given the fact that you're working in a data warehousing world where the vast majority of the work is read, is it possible to configure cache on the fly? So that you run like a batch file before you're ready to run your ETL, flip it around, run your ETL, and then change it back?
I'm going to say not to my knowledge.
You say you have to reboot?
Yeah, because that has to be done in the RAID controller while it's booting. You have to go into the RAID control and into the RAID controller configuration utility, go to the cache setting, set the cache setting, and then continue booting. I don't know of any other way to do it. Is there like with our SAN or something? Maybe, I don't know.
It'd be kind of interesting to know.
But typically, in my experience, no. And of course, another way to solve disk issues, just get faster disks, right? If you're on 7,400 speed SCSI, 7,500 speed SCSI, go to 10,000, go to 15,000. If you're on 10,000, go to 15K, right? 15K is as fast as they make now. You know, if that doesn't work, then go to SanDisk or something. You know, use SSDs or something. You know, which, you know, if you can afford those, then what are you screwing around with SCSI for, right? Get more disks. This is one of the most common ones I see. Is more disks. You'll see, you know, one of the biggest examples I have to date is at my last gig. They had severe disk queues. I mean, sustained disk queues, 24/7, of like 700 and 800. And when you look into it, they had a RAID 5 with 4 spindles, and they were big spindles, but they had a RAID 5 with 4 spindles, and they had kept increasing the size of the machine. They doubled the RAM and doubled the CPUs. Then they doubled the RAM and CPUs again and still didn't see any performance increase. Not once did anybody bother looking at any perfmon counters to see where their bottleneck was. So they were about to spend $180,000 on a brand new system that's very similar to ours, and and asked me to look into it because I got that quote and said, "My God, this is just too much." Well, you take a look at it. It's like my second week there, and I opened up perfmon and saw those sustained disk queues and said, "Okay, how many spindles do we have?" And they said, "Well, you know, we've got a RAID 5 with 4 drives in it." Are you insane? At that level of writes, you can almost get better performance out of a single IDE drive. I mean, that's just flat out, right? So what we did was we filled up a couple cabinets with disks and gave them like 30 and 40 spindles in each one and separated the data and log files, and whew, man, they were singing. So number of spindles, very, very important, okay? And if this were a database class, this would be going off in a different direction right now. Separate disks. That's another one. Really easy. So I clearly didn't go in order here of usability, right? But separate the disks. If you've got a file server and you've got a disk queue of 300 on your file server, get another array that's either on a separate controller or on a separate channel on that controller. Put half the files over there, or separate them into departments, and let that one handle that one and that one handle that one, right? What you don't want to do is take and this would just be stupid, is to take a RAID that has, say, 20 spindles in it, cut it in half, and then split the workload onto 2 separate arrays, because now each one of them has 10 spindles. Every time it read before, or wrote before, it was writing with 20 spindles. Now it's writing with 10. You're still going to have a disk queue. Now it's going to be compounded by 2. Okay? So if you split it, if you have 20 over here and you want to split it, put 20 on the other one. Or if it's a lesser one, then put 10 on the other one. But don't take something and split it in half and make 2 arrays out of it and then expect to get really good performance, because you've actually cut the performance in half because it's writing with fewer spindles now every time it does an operation. That's why it confuses people when I go to place database files, and I'll say, put the data and logs on a single partition. What? I thought you said separate data and logs. Yeah, but I've only got 10 spindles here to play with. And if I put them both on separate files, then I've only got then I've only got 5 per. And if I've got multiple database files and multiple log files on each one, I'm going to be having log file contention and database file contention over here on either one, right? So I might as well be writing with 10 spindles across the board every time I write instead of 5 spindles. As long as I'm going to have contention, I might as well minimize it by throwing more spindles at it. I realize that confuses younger DBAs when I say stuff like that, but that's just the way it is. And I think that's it for disk. Yay, we've taken up almost the entire hour with disk. Okay, memory. We'll start jumping through this. Everybody knows what the page file is. Everybody knows what virtual memory is. Everybody's good on that? Excellent. You can put the page file on any system, on any partition you want, and you can have several of them. Okay? Page file is extremely important. A lot of people, and it's true, will tell you that there is no memory that is not in page file. Okay? So if you have 8 gigs of RAM and 2 gigs of page file, you have 2 gigs of RAM. Okay? Because you need to be able to page out your memory. If you can't page out your memory, then, right? Yeah, it's useless. No, the virtual address space, the VAS. Does everybody know what the VAS is? Okay, virtual address space. That is what, and now we're starting to get into some vaguer memory concepts here. A lot more than just memory counters. But you need to understand this stuff before we actually talk about the memory counters. And the memory counters are incidental. I mean, it really doesn't matter, right? There's only a couple counters that you're really going to use every day. But I want you to understand what the VAS is. The VAS, again, the virtual address space, is what every application is carved up by the OS. Okay, when you start up an application, it's carved a certain amount of virtual memory for it to play in, its little sandbox. Okay, and that's called the VAS. The overall system VAS, Windows has 4 gigs, and it splits it into 2 2K chunks by default. Okay, so this guy right here, my laptop, if it had 4 gigs, it would split it up into 2 2-gig chunks. The first 2 gigs is for the kernel. The second 2 gigs is for user mode applications. Okay, that 3 gig switch that you use in there, and that's in here somewhere. Yeah, it's down here. The 3 gig and user VA switches and boot INI that you can throw in there, tell it to use 3 gig for user mode and 1 gig for kernel mode. Okay, then you start to get into this, and you got to be careful about that because you can really starve your OS that way. On a busy system, I would even say on a moderately busy system, you can really starve your OS if you don't give it enough VAS. So use the 3 gig switch sparingly. But on database systems, we end up doing it a lot because, we'd rather starve the OS than the database. So applications can't just use that extra gig that you give it. Okay, if you take an application, just a normal application that wasn't compiled with this large address aware flag, okay, it won't be able to access more than 2 gigs. Okay. Now, the difference between 32 and 64-bit. Does everybody know the difference? I mean, physically the difference between 32 and 64. I'll say it anyway, because everybody might not. 32-bit systems have a hard-coded memory accessible range of 4 gigs. That's why Windows starts out with 4 gigs and it cuts 2 gigs right down the middle and splits it, right? 32-bit can't address more than 4 gigs. Okay? 64-bit can. So it's not a limitation in Windows. It's a limitation of the address space itself. You can't. There aren't enough numbers to go over 4 gigs. Okay, and so that's why 64-bit is so popular, because you can run applications with tons of memory, and they don't have to be large address aware. They can just access that memory. Okay. I think that's going to lead us into AWE. Does everybody know what AWE is?
Something windowing extension, but I can't remember what the A is.
It's addressing Windows extensions. And what that is that is a modern day high mem sys for those of you who started long ago, right? And that's exactly what it is. It allows you to take a 32-bit system and put more than 4 gigs of addressable space on it. Okay, and what it does is it does that by mapping. So it'll take a 32-bit address and it'll map it to a 64-bit or to an address up here in physical memory, right? And it's only physical memory. It's non-paged, so you don't have to support it with a paging file underneath because it can't be paged. It's non-pageable memory. Okay, and there is a hard limit on how much you can AWE. You can only have so much usable AWE memory. The reason for that, and I forget what the number is, it's something like 16 gigs, in that neighborhood. I forget exactly. But the reason why is because AWE is going to use that translation table. Well, it uses a 1 gig translation table. And again, you come across the same addressing problems that you have. There are only so many entries that can fit in that table, and then that's the end of your addressable AWE memory. Okay? I don't know if I actually wrote down performance counters. Nope. Okay, so, and actually we're almost done. Go over a couple of the Windows counters here, or the memory counters. So we'll get off processor. And since we're here, first we'll talk about page file. These are very self-explanatory, percent usage and percent usage peak. I always pick both of them because I not only want to know, how much it's being used right now, but I want to know what it spiked to, right? And of course, did we go over the difference between total and individual counters last time? If I had several page files, it would list each one of them individually, but then I could also take a total collectively. It's the same thing with every single counter, right? For percent disk time. Oh, I love that. See, and that's another problem with percent disk time is it's the recommended counter. People use it all the time because it's recommended. But you've got a total here. That's going to be a total for all of your disks. I happen to have only one disk in this system. Or you could see C, D, E, F, G, H all the way through Z, right? Individually to see which one of them is causing the queue. But typically, you'll come up here to total to see if there's a disk queue at all, and then if there is, then you'll break down into the lesser, into the individual. It's every counter has a total. If I come to processor, I've got a total for processor, or I could look at each individual processor. Okay? So, same thing with memory. Or anyway, so paging file, when you're looking at it, grab both of these. Databases don't page that much, but a lot of the stuff you guys do. Okay, Windows itself pages. The database doesn't, but you guys will probably get more out of this than I do on a regular basis. And memory, I said memory, there it is. Okay, then it doesn't have it because you've only got one set of memory, so there's no such thing as a total memory. You're not looking at the individual DIMMs inside of your box, right? So pages per second is what that one's looking at, is what that one recommends. And that goes directly with the page file I just said, right? How many hard page faults are there? And that's a hard page fault, right? A hard page fault is when it has to actually go to disk to get the requested data. So it expects to find it in memory. It's not in memory. It has to go to disk and fetch it. A soft page fault is when it just gets moved to a separate area of memory. So it pulls it from one memory location to another versus the disk. Right.
So is there an advantage looking at page read or page write?
I suppose it depends on what you're looking for. I've never had to break it down into page reads and page writes. If you come here to the explain.
I mean, that will give you some indication with respect to disk bottlenecks.
which the
Because
disk
if
was
you are
read to
going to a
resolve
hard
the page
fault,
fault.
then it does give you an idea of how fast it's pulling it.
Well, it says here, it's the rate at which the disk was read to resolve hard page faults. So, and I would imagine that the other one is how hard the disk worked to write the page fault, right? You've got high paging. Unless you're like on a super system, it doesn't matter if the disk is spending most of its time reading from the page or writing from the page when you're doing a page fault. You're paging. Solve the paging problem, not the read or the write problem within that process. I've never had to use that, so right, it doesn't matter. You've got high pages. Take care of your paging problem. Fair enough. And the only other ones that you're really going to be concerned with, committed bytes in use is okay. Available bytes, I like available megabytes because available bytes is just too much math for me. When you get these numbers that are 12 and 15 digits long, my head just goes, okay, available megs, that's what I need, right? Now remember, that's available megs, right? So the bigger number, the better, okay? As that number starts to dwindle, then you're starting to use up your memory. Okay, and that's one of the ways that you diagnose memory leaks is when your memory gets smaller and smaller and smaller and smaller and smaller, and you see an application taking up a lot of memory, and you kill it, and the memory either stays the same or it still keeps getting smaller, then you've got a memory leak. That application isn't releasing its resources. Okay, so available megs and pages per second. Really don't need too much more. You just want to see if you have enough memory on the box, right? I mean, what do I have left? I've got this many megs left. Okay, great. So memory is pretty easy. And I didn't write this down. I don't think I've got it written down anywhere, but we'll go ahead and do CPU as well. Processor. Again, processor time. That one shows up in Perfmon by default, so you don't have to select it. And if you try to select it, it'll tell you that you've got that it already exists. And I lost it. Okay, privilege time versus user time. That's kind of a tough one. I was talking Kim through this a while back. How to explain that? Privilege time is the amount of time that the CPU uses in kernel mode. And user time is obviously in user mode. Okay? If you have... Is that in here? No, that's in the other one. Okay. You want to spend more time in user mode than you do in privilege mode. Okay? Because when you're in privilege mode, that means that you're doing OS level stuff that's taking a lot of extra work. You shouldn't spend more time cleaning house than you should spend living in the house, right? And then you can look at context switches, which I think is a system level counter. God, I could have told you before I had to do it on film here. Is it system or server? Context switches per second. Context switches per second is how many times it switches from kernel mode to user mode. And if this is kind of where the baseline gets really important, because if you don't know what your normal level of context switches is, you're going to look in there and go 16,000 per second. My system is sick. I need help. When that's perfectly normal on our warehouse, 16,000 a second is nothing. I mean, we average that all the time. Now, is our system born sick and stay sick all the time? Possibly, but it's normal for our system. Remember, we talked about that last time. It doesn't really matter what the counter is supposed to be. It's what is the counter usually on your system, right? I wouldn't even know how to calculate. I don't think there is a way to calculate what your context switches should be for any given system. You always go by baseline. When the system's running at its very fastest, which is usually like when it's put together, right? When it's at its very fastest and things are running really, really well, that's going to be your baseline for things like your context switches when you have no other way of finding out what it is. There's no way to calculate that, right? But context switches, if your context switches are 3 and 4 and 5 times what they should be, say if you expect to see 1,000 and you're like up into 7 and 10,000, a lot of times that's a bad driver. That could be a corrupt driver. That could be hardware that's failing because it's having to do too many context switches to communicate with the disk now. right? Too many context switches to communicate with the video card, something like that. But usually when I see too many context switches, that's almost always, I can't think of an instance off the top of my head right now where that's not going to be some kind of driver or hardware issue. So instantly say, context switch, hardware guys, go. And then you just kick back and say, I solved the problem. Right? Tell them you got a lot of context switches and then let them deal with it. They've got deeper diagnostic stuff that they dig into, right? And those are the major counters. You know, like I said, these are such extreme basics, and later on, after we get a couple SIS classes out of the way, we can revisit these, and I can show you. Remember, we were talking about last time how to actually go in there and create the performance logs and log them to a file. And maybe next time I can actually follow that all the way through, and we can do some logs and do them and put them in a file, and then import them into Excel, and then do the equations and show you how to actually interpret these things and learn how to correlate them and see, you know, how you can look at one counter and see if that's going to feed another counter, and you know what I mean?
Yep.
So we can follow that to its conclusion, maybe even wrap a small SRS report around it or something, you know, just to show you what's possible, which I'm sure is going to hit production. I do a small example in here, and yes, it'll hit production the next day. But that's all I've got for the basics. I don't expect you to remember everything, but that's why we're recording it too, so you can go back and listen to this as much as you want.
I have to see how much memory is left in our brains.
Yeah. Well, you know,
It's cash.
it's funny. The studies I've seen show that no matter what amount of material you're presented with, people on average remember about 20%, right? So I like to give tons of information, because that means you'll remember 20% of tons versus 20% of a little bit. And the more, and you don't have to remember this. Like somebody said it last time, it may have been Richard. It doesn't matter if you remember it all. The fact that you know that it exists and that you know what direction to take it. Now, he said something about this, and I don't remember what it is, but hell, man, you got the internet now. I mean, even if you don't remember exactly what I said, you know it exists, and all this information is freely available.
You just
And
need to know so and so solutions available. Then
Yeah.
you can explore it. What is the actual
Yeah,
solution.
exactly. And I mean, between, you know, higher level techs and Microsoft forums and other forums, and if you guys really want to get into performance monitoring, I mean, really learn how to do it well, get the Server 03 resource kit. There is the book in there on performance tuning, written by Mark Friedman, and he wasn't at Microsoft when he wrote it, but he's at Microsoft now, and he's the one in charge of putting together a lot of the performance framework and the new .NET framework. And he deals with the performance guys and all that all the time, and he's the one actually coding this stuff. And he wrote the performance guide for the res kit, and it's an excellent book. I mean, it's got just dozens of pages with all of the counters listed, their frequency, the issues that there are with them, if there are any holes in their collection methodologies, he lists that. I mean, it just on and on and on. I mean, it's really, and it's still considered today to be the de facto resource on the performance counters, because he gives all the information that all the other books don't give. So it's an excellent book if you get a chance to pick it up. But you can't pick it up. You have to pick up the res kit, which is like 7 volumes of book. But all of them are phenomenal. But that one in particular, if you want to learn this, go to that. He does have another book out on 2000 performance tuning. But some of the stuff has changed from Windows 2000. So, you know, go 2 OSs back at your own risk. You know, but you'll get the concepts, and then you can upgrade. You know, you can update it with the thing, but you can't just buy the performance book out of the res kit. Anyway, okay, that's all I got.
We appreciate it, Sean.
Yay.